In Chapter 7, Section 3, we're going to talk about something called the discriminant. And for background on that, sometimes we don't really need to know the actual solutions to the quadratic equations. We just need to know what kind of solutions they are. For instance, do we have one real root, two real roots, or two complex roots? And we'll find out about that one as we take a look at the examples below. To answer the question, though, if we have one real root, it's a double root. And why we may not need to know exactly what they are is if we're just approximating the graph. If it's one real root, we know that our graph would be tangent to the x-axis at one point. If it's two real roots, that tells us that our graph crosses the x-axis at two distinct locations. And if we have two complex roots, that'll tell us that our graph does not cross the x-axis at all. So anyway, let's get back to finding out what kind of answers they are. So let's start out with our quadratic equation. We're looking for two solutions, and a is 1, b is -5, c is 6. Put this in the quadratic formula by substituting in the numbers. And I'm going to go through this fairly quickly because we did the quadratic formula in our previous episode. So it's going to turn out to be 25 minus 24. And the main thing I want to point out here is that the radicand is a positive number. Now, in this particular case, when we have positive 1, the square root of 1 is 1. So my two answers, rather than leaving it as 5 plus or minus the square root of 1 over 2, I need to simplify it. So it could be 5 plus 1 over 2 and 5 minus 1 over 2. And by the way, if I have such easy answers like this, that means I could have factored it as well as put it in the quadratic formula. 5 plus 1 is 6, divided by 2 is 3. 5 minus 1 is 4. 4 divided by 2 is 2. And we have two real roots. And in this case, they turn out to be nice integers. But they could be irrational as like the square root of 3 or the square root of 2 if that were the case. But here, as we color code this in this brown, we have a positive number as the radicand. We end up with two real roots. Let's look at another example and see what happens. So if we go through and say a is 1, b is -4, c is 4. I know it would be easier to factor this, but I'm just practicing the quadratic formula since we learned that. Replace all the a's, b's, and c's with 1, -4, and 4. Do some simplifying. Notice what's going to happen under the radicand here. 16 minus 16 is 0. And in this particular case, we have 4 plus, the square root of 0 is 0. 4 plus 0 over 2 and 4 minus 0 over 2. And in either case, 4 plus 0, 4 minus 0 is both 4. 4 divided by 2 is 2. And so for our two solutions, two roots that we're looking for, according to the fundamental theorem of algebra, we have a double root. So in this case, we have one real root, but notice that it's the root x equals 2, and it's a double root. Can we predict when that happens? Yes. When the radicand turns out to be 0, we're going to look for one real root. That's a double root. All right, let's take a look at this next example and see what we're going to end up with. And let's put those coefficients at a is 1, b is 1, c is 1. Let's put that into the quadratic formula and start simplifying. And notice here under the radical sign, we have 1 minus 4 is -3, and we're getting a radicand that's negative. And so what I have here is the square root of -1 is I, and the square root of 3. And it looks like because we have I in our answer, we have two complex roots. And can we predict when this happens? Yes, it's when the radicand turns out to be a negative number. All right, so we have some observations that we can make. Let's try to summarize what was true. When the radicand was positive, we ended up with two real roots. When the radicand was 0, we end up with one real root, which of course is a double root. When the radicand was negative, we have two complex roots. And so since that helps us predict what it's all about, the radicand, recall, is b squared minus 4ac. And we call that the discriminant. To discriminate has some bad connotations, unfortunately, in today's society, but to discriminate really just means to be able to tell a difference between. It doesn't mean treat the people differently as we uncommonly see in life today. So to discriminate is to discriminate whether our answer is going to be 2 real roots, 1 real root that's a double root, or 2 complex roots. That all happens with the radicand, and what's under the radical sign in the quadratic formula is b squared minus 4ac. So we call it the discriminant because it helps us determine what kind of answers we're going to get. And so we don't always need to know the actual solutions, just what kind of solution is. And you know that we're looking for that when you see this kind of phrase. Determine the nature of solutions. Determine the nature of solutions. That means, are we going to have 2 complex roots, 2 real roots, or 1 real root that's a double root? So that's what we're looking for when we see that instruction. Alright, so all we need to do then is to calculate what b squared minus 4ac is, determine whether that's positive, 0, or negative. So let's practice determining the nature of some solutions, starting with example 2a. A is 3, b is negative 7, c is 5. So b squared is negative 7 quantity squared minus 4 times a, which is 3, times c, which is 5. Negative 7 times negative 7 is 49, and we have 4 times 3 times 5, which is 60. And sometimes we don't really need to know what this number is, although our book's going to ask us that. I just know that 49 minus 60 is 11. Negative is what I was trying to say. 49 minus 60 is negative. In this case, it's negative 11. So since it's negative, we know that we're looking for 2 complex roots. 2 complex roots. Alright, let's look at another example. In this particular case, 2x squared minus 13x plus 15. A is 2, b is negative 13, c is 15. We're going to do the b squared, which is negative 13 quantity squared, minus 4 times a, which is 2, times c, which is 15. Simplify that, 169 minus 120, and that's a positive number. So what we know here is that we have 2 real roots. Our book likes to go on further when we have real roots and ask the question, well, are they going to be rational or irrational? And so I do need to know that this number is more than just positive. I need to know what it is. 49 happens to be a perfect square. Remember, the radicand was under a square root sign. If we took the square root of 49, we would end up with 7, so we would end up with 2 real roots, and it would be rational numbers. Now, if this was a number like 47, it would be 2 real roots, and they would be irrational, since the square root of 47 cannot be simplified. Alright, in our next example, we have x squared plus some interesting coefficients, 2 square root of 3 times x minus 1. So a is 1, b is 2 square roots of 3, c is negative 1, and we're going to simplify and evaluate b squared, so 2 square roots of 3, quantity squared, minus 4 times a, which is 1, times c, which is negative 1. Now 2 times 2 is 4, square root of 3 times the square root of 3 is the square root of 9, square root of 9 is 3, and 4 times 3 is 12. Negative 4 times 1 times negative 1 is positive 4, and 12 plus 4 is positive 16. And so we have 2 real roots. Again, they both happen to be rational numbers. The square root of 16 gives us 4. If that were the square root of 15, it would be irrational. And I didn't do the example here, but if we ended up with 0, then we would have 1 real root. That's a double root. And that's our look at the discriminant.